Right, welcome to the second lecture in the lecture series on the future of AI, self-supervised learning and foundation models. Right, so this is where we learn about the fundamental and deep revolution that's occurring within AI right now. So today we're going to go through the different algorithms that we use within self-supervised learning and foundation models. And we will go through a lot of different approaches, and don't worry if you don't get everything. This is about exposing you to these different approaches. And as we learned about last time from AI, right, we never really fully understand something, just get more kind of familiar with it. So that's the plan here, just try to get more familiar with these concepts. And last time, to summarize and recap a little bit, we provided a short and succinct answer to what is self-supervised learning and foundation models. We then went on a philosophical and historical journey and asked how the world is structured, because that informs us how we learn in the world. And we went through especially supervised learning and reinforcement learning and concluded basically that self-supervised learning is the only viable option because supervised learning is too label intensive and too much manual work, right? Doesn't generalize well. Reinforcement learning is too risky. And you make no progress if you don't have a basic world model, right? If you have no starting point, if you're a blank slate, you make no progress. So self-supervised learning is the only viable option, right? Where we learn from just observing the world. And we went through some applications, right? So what we said last time was that in self-supervised learning, we learn from just observing context, we contrast concepts, etc., and we don't use any label data, which means that we don't have to have human beings in the loop, so we can train a lot of data, and there's no limit there in some sense. So we build these big foundational models. And that the meaning that we get, right, from learning from observation is this kind of relational meaning, where we learn what a dog is by contrasting dogs with other concepts as we observe dogs, right? That a dog is something that's walked by an owner with a leash. It might have antagonistic relationship with the cat or cats, and it might chase frisbees when those are thrown, right? That we define meaning in this relational sense in the company that a dog keeps. And yeah. So today we will go through the algorithms. We'll start off with natural language processing, NLP, and language. We'll cover CLM and MLM. So CLM is causal language modeling, and then we have mass language modeling. Then we'll talk about contrastive learning, puzzles and games, denoising and diffusion, autoencoders, GANs, so generative adversarial networks, and generative approaches in general. And then we'll see how those are applied and kind of what the implications are around these approaches. All right, so let's get started. So we'll start in language, and this is basically also where self-supervised learning and foundation models actually started off. So it's a good place to start. And also, as we talk about language, I want you to kind of keep in mind that language is special. It's man-made, right? We have designed language to serve a purpose for us. And we don't only communicate using language, we also think in terms of language. And I think it's a really good chance that if we ever come across a different intelligent life form, they would also have a language, even though they don't communicate with each other. So somehow, language perhaps is a requirement to have intelligence. And it's something that hopefully I'll be able to communicate by the end of this lecture. And really that language is an efficient universal medium for transporting and verifying ideas. And we'll try to make that tangible. All right, so when I started my career at Stanford a long time ago, like 6 years or something, then there was basically in language a separate research team per different language task, right? So you would have one team, one data set, and one model that focused on translation, going from one language to another. You have a separate research team, model, and data set around question answering. And then you have a separate research team and data set and model when it comes to classification, right? Classifying a product review as positive or negative, for example. And then we have a separate team, data set, and model for prediction and generation, right? Like your autocomplete on your phone, etc. So these would be very isolated efforts, and people started asking themselves, like, are we perhaps spreading ourselves thin here, right? It seems like we're all doing something that's around language understanding. Can we perhaps try to optimize a perspective here that learns, language understanding in general, so we can pool our efforts together? So that's what we started working towards. Right, we don't have a separate brain for each specific language task. We have one single brain, and if we can perhaps pool data together and pool our efforts together, we can make more progress. So how can we try to accomplish this, right? How would this pipeline look like? Let's try to explore. So in some sense, we want perhaps to be able to have a general model that looks at some language or text, for example, right? Learns to extract the meaning of that text. And then we want to be able to feed that meaning in all of the different tasks that we care about, right? This is called downstream tasks. Of course, this looks perhaps sensible and a good starting point, but it's still very abstract. So let's think about, for example, meaning as a first step. Like, how do we even think about meaning? How do we represent meaning and communicate meaning? So we can use it and give that information to our downstream tasks and models. So let's start looking at some words and try to understand if we can encode the meaning of these words, right? So here we have cat, kitten, dog, and puppy. And just to understand that meaning is very nuanced, let's add some pictures to help us out, just to kind of, that we understand that there's a lot of components to these different concepts. And so clearly, if you want to understand the meaning and encode the meaning of these different words, there's a strong relationship between cat and kitten and dog and puppy, because they pertain to the same species, right? I think we all agree that those should somehow be close in meaning because they refer to something that's very similar. But also, right, there's more nuance here, because somehow kitten and puppy are also related and quite similar, because they both refer to cute baby animals. So we also need to be able to encode that, right? That there somehow are words that refer to babies and small animals, while the other ones perhaps are more adults. So if we would just perhaps describe these different words with a single digit, we would have to pick and choose, right? If we want cat and kitten to be close and with a single digit for each different word, we were able to attain that, right? And dog and puppy to be close. But then how do we get puppy and kitten to be close as well in some sense, right? How do we communicate a lot of these high dimensional, meanings? So that's what we'll do, is that we'll say, like, it's not enough with a single digit for each word. We'll represent them with multiple digits, right? A high dimensional vector or tensor, which is an array of numbers. And right now here, all these numbers are the same, but obviously they would be different in the real case. And then we can use different positions in this array to encode different information. So for example, we can have at the first number, we can have the species, and the third one we can have age. And now we can communicate that the two words might be similar in terms of the age that they refer to when it comes to animals, and one of the digits represents the species, right? So we kind of were able to solve this problem. But this is great, so now we at least know not how to learn this meaning, but how to represent meaning if we can learn it. And this is for words, of course, but clearly we cannot perhaps do this just for words kind of globally, because meaning is extremely contextual, as we learned in our last lecture, but it is so true for language, right? Here we have bank, the same word appearing in two different concepts and meaning something very, very different. So in a river bank, right, you have the edges of a river, and a financial bank, you have something that pertains to loan and money. So these are very, very different, and what allows us to understand how to interpret the word bank is based on this financial river, right? So we cannot let a model just feed in a word and encode that to a vector high dimensionally and solve the language, right? Because we don't think in terms of words, we think in terms of sequence of words. That's how we interpret things. That's how we convey meaning in text, is by these contextual sequences, that where every word matters and affects the interpretation of the other words. So we have to have a model that creates these embeddings or vectors of meanings, right, numbers, from fitting in a sequence of text, right? So it would have to be able to look at riverbank together and encode that to the right meaning, and it would have to look at financial bank together and encode that to a different meaning, right? So that's what we need to accomplish. And then the question is, how do we actually accomplish this? How do we train a model or a computer to learn to extract this sequential contextual meaning from text? Right. And here really the problem is the cue to the solution. That we saw that language is so contextual, that also it's so contextual that also allows us to pick up the relationships, because it is so embedded in the structure of language itself. So what we'll do is actually quite simple, and we'll think about defining meaning by the company it keeps, this kind of co-occurrence and contextual approach that we've seen before. And this perhaps takes some time to understand why it works, but intuitively it should make sense that if we now just take text from a line, we just download as much text as we want to, and we take a sequence and we just randomly mask out a word. And then we train the computer now to predict that masked out word from the context, right, the surrounding words. And if it's able to start doing that well, it needs to be able to pick up the meaning of these words, right? So if it's able to say that when it sees a sentence, I went to the beep bank for a swim, and if it's able to predict that the masked word here is river, right? It somehow understands how to interpret bank in this context, because it sees the cue for swim, and then it knows how to interpret bank, and bank in this context refers to the edge of a river, so it will predict river, right? And by doing this in a lot of different contexts, it starts getting this understanding of language and how to embed the meaning implicitly. Similarly, if it is fed the masked sentence, right, I went to the beep bank to deposit money. If it's able to predict financial here as the masked word, somehow it's able to interpret bank from money occurring in the same context, right? So of course these are kind of simple examples, but they're fed 1,000 sequence-long words or sentences or text, right? And they mask multiple masked word, so it becomes very difficult. But when it starts to do that better and better, it picks up a really powerful kind of understanding of language, and you force it to create vectors in the process, and these embed the meaning of these sentences. So it's extremely, extremely powerful, and it really rests on this assumption that meaning is defined by the company it keeps. All right. So this is great. We now have defined meaning to these high-dimensional vectors, a sequence of numbers, right? And we decided we'd have to embed sequences of text, right? Words, not a single word. And we can now have a procedure to learn to do that. So we're in a great place. And this is what we did in this field, right? So we now have this brain that we can train on just text in general, as much text as we want to, huge models, a lot of parameters and a lot of data. And we can then get any text that we want. We can embed it to some vector that conveys the meaning of this. And then we feed that to the downstream tasks that we care about. So this is awesome. But if we dig a little bit deeper, we still have some challenges. If we look at these different downstream tasks that we considered in the beginning, question answering, for example. So let's say you have a question, what is a riverbank? And you're able to use our model now to embed that into a high-dimensional vector that conveys the meaning of that question. That's great, but how do you generate the answer, right? It's not clear. Like if you have a few candidate answers, you can embed those answers as well and then see which ones are closest in this meaning space, right? And you hope that the answer to the question is closest in some sense. It actually works really well if you have candidate answers to consider, but if you don't, you're kind of screwed. You have to engineer something that allows you to train on your downstream data of actual question answering examples, and use this model as a starting point, but to additionally train and build something to solve this task. Similarly in translation, right? Now we can take some text and we can embed the meaning of it in a very sophisticated way, But how do you generate the translation of some text just because you know the meaning of that original text, right? The task doesn't just solve itself. We still have a lot of engineering to do here. And right, the same, maybe the only one here that's really simple to do here is classification, right? Where you can take a product review, you can run it through our model, get this high-dimensional vector of meaning, and then you can quickly kind of try to infer what in this high-dimensional meaning conveys or represents positivity or negativity. That's actually quite straightforward if you do some hard work, right? But that might be the only one that's quite straightforward. In all these other cases, right, when we come to this vector, we somehow have to define additional models that we continue to train on some downstream data to learn to do these different tasks as well, right? So there's somehow a divide between our pre-training on just text to learn this big model and the different downstream tasks that we care about. I mean, it might not be a huge challenge, but it is still a challenge. So this also is an extremely important aspect within self-supervised learning foundation models. We have the pre-training process, where typically, just learns from a ton of data in this self-supervised fashion and learns a lot of different understanding of the concepts involved in a relational sense, right? And then you want to use that model and understanding that you get to solve a lot of different tasks. You want to plug this model in everywhere. But the challenge is that, of course, you want to pre-train in data and in a setting that's very close to the downstream tasks you care about. You want the difference between how you do your pre-training and the downstream tasks you care about to be as small as possible, right? If we take the example of learning how to drive a car, if you want to learn how to drive a car by observing other people driving cars, right, somehow you want to make your observations as relevant as possible. And that whole process is possible and informative, so when you actually sit down in that car to do it yourself, you're as prepared as you can be. Even though it might be impossible to completely simulate the process of driving a car by just observing it, you want to get as close as possible, right? Because you want to be as prepared as possible. And definitely kind of a similar challenge here is simulation versus reality. That when we learn something, we might be in a more simulated environment because that's the only thing we can afford or have access to, but we want that to be as close as the real environment that we expect to actually, find ourselves in when we do this in the real setting. So this is definitely something that we spend a lot of time to think about in self-supervised learning. How do we make the divide between the pre-training and the downstream tasks as small as possible to save time, to save work we need to do, but also to get better performance? Because really what we care about is all this different downstream performance. We don't care oftentimes about the pre-training task itself, perhaps. As we go further here, we can maybe pull this as close to as possible so they're very, very similar, but we'll see. Okay, so great, we have a setup, and we find a little bit of a challenge that we can now create these high-dimensional vectors of meanings from text, and we can plug them in a downstream task, but there's still a divide between these high-dimensional vectors and how we actually solve a different task, how we generate answers or translations. But we also said that language itself conveys meaning, right? That's why we created language, because it conveys meaning and helps us communicate meaning. So why do we even go through these high-dimensional vectors? Can we just kind of go from text to text, right? So here I think it's quite helpful to think about perhaps if you would look up a word and try to understand the meaning of a phrase or a word, right? You wouldn't want to have a high-dimensional vector of that word. You would somehow want to have a definition of it, right? You want to map this sequence of words to another sequence of words, that explains what that means. And maybe we can start kind of training these models in the same way, text to text, and that might be more helpful. Because when we think about it, right, text is a very flexible instrument to encode information. So maybe we can encode all of these different downstream tasks just as text-to-text problems, right? If we, as we did, if we just prepend the actual kind of task, right, or we just encode it somehow with a question mark, for example, there's a question, we can just say, like, answer this question, what is a river bank? And what we'll expect is just literally the answer in text. So it's a text-to-text problem, right? Translation, it's also a text-to-text problem. You just say, translate this to German, you provide the text, in a single text, and then you expect to get the translation on the other side. For completion as well, you can also encode this as just a text thing by prepending the task that you care about, and then you want the actual response, in text as well. And in classification as well, you can do the same thing. You just ask for the classification or the sentiment of a sentence, and you want to get the real answer in text. So if we can change now our pre-training task to also be text-to-text, instead of using perhaps these vectors that we care about or define, then at least the downstream task and the pre-training setup is the same, because they both go from text and inputs text and generates text. And if you then define all the downstream tasks also as inputting text and generating text, at least then they're similar in that setup, right? Maybe they train on different things, but they're similar in terms of the engineering. So this is what Google did with their T5 model, which works extremely, extremely well. And they used this text-to-text approach where they define all the different tasks that they care about as text-to-text, and also they pre-trained using text-to-text. And specifically how they did that was by, and it's very simple actually, it takes a lot of tricks and engineering to make it work well, but the fundamental approach is very simple. Now instead of just masking single words, they mask a contiguous sequence of words within a sentence or a sequence, and then they try to predict that whole sequence, right? The non-corrupted sequence in some sense. And by doing this, they actually basically get the same understanding as we did before, but they do it in a way that's text-to-text. And then when they want to fine-tune, they basically have the same setup. They can pull all the data together for all these different tasks, train it together, and there's much less work to be done because they don't have to add models or architecture to the downstream task because they already are in the same format. All right. So I also want to mention, when it comes to language, two major approaches, which is masked language modeling, which is basically what we've been talking about right now, versus causal language modeling. And in masked language modeling, we randomly pick a word, we mask that, and we try to predict that from the surrounding words. But in causal language modeling, we always mask the last word and only try to predict the last word based on previous words. And it might seem strange, why would we only mask the last word? And if you remember from last lecture, now that you know that we learn meaning contextually, it perhaps makes sense to mask things in the middle, because then you get correlation between words that appear in the future as well as historically or behind, right, in this sequence. Because it turns out, this is a little bit technical, but how they're implemented is that in masked language modeling, each word, when it embeds itself, or each word is able to attend or take in consideration all the other words in the sequence, words in front of it as well as word behind. And since it has more context to use to embed itself and correlate itself with, it should get a better and more sophisticated understanding of meaning, right? In causal, by virtue of the technical details of causal language modeling is implemented, it's only allowed to look backwards. So it basically only have half the context, so it should be worse at understanding its own meaning, right? It's helpful to understand what words that you correlate with that comes after you. And this is true. Masked language modeling basically works better for almost all tasks, because it's able to use more context and information to embed itself and correlate with, so we'll get a better understanding, right? The company of words it keeps is bigger because it has a more clear vision of it in some sense. But because how causal language modeling is implemented, and we'll talk about this in the next lecture, by transformers, it's better at one single task. And that's generating the next word based on previous words. That's almost the only task it's better at, but it turns out that's perhaps a very, very important task. Because if you think about this again, we have this text-to-text, problem. But what if we just have a model now that's able to generate the next word based on the previous words, and it can do this incrementally, right? Successively, word after word, generate text. If we give this model it's really, really good, and we say, answer this question, what is a riverbank? I mean, if it's a good model that's able to generate the next words optimally, it should provide the real answer. If we just say to the model, like, translate this to German, the following text to German, right? My name is. If it's really good at generating the next word, it should generate the actual German translation. Similarly, right, if we do this for also other tasks, it should be able to do all the different things, because these are perhaps the most reasonable completions of our input text, right? And this is exactly actually how ChatGPT is trained. This is the core fundamental technique of how ChatGPT is trained, and extremely powerful. I mean, of course, it solves this very kind of simple task, right, by just predicting the next words. And it does much, much more, and we'll talk about this in the next lecture. But it's extremely, extremely powerful, because now there's literally no difference whatsoever between the pre-training and the downstream task. If we do it really well, we can just throw away basically our downstream data. Because now if we train on all this text online, as much text as we can with as much parameters and compute as we want to or can afford, then it gets really good at just predicting the next word from the previous word, generating text, and it basically becomes a multitask solver automatically. Because there's no difference between how we define this different downstream tasks in the pre-training, and we can all encode them in the same format, which is just generate the next word based on previous words. So it's extremely, extremely powerful, and explains the success of the GPT models. All right, so to summarize the language journey here, so we define meaning by the company it keeps, because meaning really is contextual, right? Language is where it started up, because it's so obvious in language that words mean different things depending on where they appear. And that's also the cue of how we can learn these things, right? But since it is contextual and relational, we need to have multiple digits to encode meaning of concepts and text, right? It can't just be a single digit. So that's good, and we could use that, and we started using that in this field. But then we said that it's good if we can align the setup and the architecture for the pre-training close to the downstream tasks that we care about. And then maybe text-to-text models is a good way to do that, because we can encode our downstream tasks as text-to-text problems, and we can pre-train in that way. And then we end up saying that maybe actually all of these tasks can just be phrased as generating the next word based on previous words. And now there's basically no divide between the downstream and pre-training. All right, so let's move on from language and go into vision. You can definitely try to apply similar techniques. You can think about images as just top to bottom, left to right sequences, and you could try to predict the next pixel based on previous pixels. And as you see here, actually it works quite well. And as it does this, right, it has to implicitly start to understand different concepts. Because if it sees the eyes and the ears of a cat, it needs to understand a little bit what a cat is to be able to complete it, right? And now you see different seeds or random seeds, right, of how it completes this, but it needs to understand, these different concepts able to generate them. It needs to understand crosswalks and shadows, etc. as well, right? So it has an indirect, implicit understanding of a lot of different phenomena in the world. But this is not kind of really what we're using in vision right now, or that's not really state of the art. Instead, what works really, really well in vision is learning by contrasting. This is contrastive learning. And we talked a little bit about this in last lecture as well, but it's extremely general and powerful. And one of the core components within contrastive learning is positive pairs. And here we just say that we believe that concepts that appear in the same image are more related and close to each other in meaning than concepts that appear in different images. And that, of course, is not always true, right? There can be a dog in this image, there can another image where there's dogs. But when you have enough data, this is true statistically on average. When you just take two different random images, it's more statistically probable that the things that appear in the same image are more related than those that appear in different images. And of course, so what we do is just that we can now download as many images as we want from the internet online. There's unlimited amount of images. And we just take an image, we'll create 2 different crops randomly, and we'll say, okay, you guys are more related than crops on other images. And kind of it's defined by this co-occurrence, right? And you want to be able to say as well that if in this example of this owner or human being with a leash, right, that it's further away from something else. You really need to contrast this with something. Because if you just say that you want to map it close to things that appear in the same image, right, basically it can collapse, because if it's not also forced to push it away from other things, the model can just learn to map everything to the same representation, and then everything will be close, right? And closeness has no meaning. So for closeness and similarity to have meaning, you also need to have dissimilarity and distance, right? So that's why you need to be able to say, like, well, I am closer to a dog than I am to a woman or a cat. And also what I think is worth pointing out here is that you actually don't have to appear in the same image as something, but you can still be very, very similar in terms of meaning, right? It's like people that share a lot of friends are similar people. So even if I have 2 different species of dogs, right, that never appear in the same image, as long as they appear together with other similar things, right, then they become close. So if you have 2 different species of dogs and both appears with frisbees and owners with leashes and dog food, then they will be close because they appear in similar companies, in contexts. So it's a very, very powerful way to learn meaning of visual concepts. And a little bit more specifically, how the model is trained is that it's basically fed these different crops. It doesn't know, right, which ones are paired and which ones are not paired. We only know that because we created data, but the model doesn't know. That's how it learns. But it's feed these options, and we say, like, well, look at this crop of this human being with a leash. Now, when you've seen this, tell me which one is its positive pair, and tell me which ones are its negative pairs. That's how it's trained. And here, if it's able to understand this thing, right, it understands that, okay, if a person is walking with a leash, it's probably a dog at the end of the leash, not a cat, right? And it seems sensible. And this is perhaps quite simple, but in the real case, it has, one positive pair to locate among 10,000 negative ones, for example. Then it becomes really hard, and to do that well, it has to have a really sophisticated understanding of visual concepts. And of course, we can do this anywhere, basically, where we're able to create positive and negative pairs. We can learn by this contrasting. So we can do this also for text, where we just take a text sequence. We create basically 2 different augmentations of version by just creating 2 different masks version, right? And then we can create a negative pair by just sampling a random sequence somewhere else from the internet, right? And then we'll train this contrastive setup to push these representation to identify the positive pair among the negative pairs. And actually, this works really well for language as well. So contrastive learning is a very general way of learning meaning in a lot of different modalities. All right. So now we've talked a lot about defining meaning by the company it keeps, contrasting concepts, co-occurrence and correlation, etc. Now we'll try to take on a different set of glasses and just think about the task itself. We'll just think about defining games or tasks for the models and computers to try to solve, and hope that they learn something about these concepts involved by doing that, right? So we want to have defined this simple task that we can define on data without putting a lot of effort into it. And if the computer solves it, it needs to have a sophisticated understanding of the concepts involved. That's how we think about it now. We kind of forget about contrastive learning correlation, that we just think about different tasks that might be interesting, because it might help us to think about self-supervised learning a little bit more broadly. I mean, it might be equivalent, but it can just allow us to be creative. And here, right, meaning now is just defined by how it helps us solve the task. So if we go back and think a little bit about language, we can, for example, just take a sequence of text, right? They have a real order when it comes to us from the internet, right? But then we can scramble those, feed it to a computer, and tell the computer to put them in the right order, right? It has to learn to take a shuffled sentence and correct it. And in order to do that well, right, it needs to understand, again, somehow the meaning of language, because it really helps understand the meaning of language and words and text to be able to put it in the right order and to get a contextual understanding. Actually, that's true. It does. It's basically able to very, very accurately take text, put them in the right order, and get the real text as if it was given to it, as the right order. So what recent work has shown is basically, for a computer, they don't even need to get the real order of text. You can just get the text scrambled and all the words, and it will almost do as good as a job as it would if you got the real correct order, which is quite fascinating. And we can, also do this for images, where we can take an image, we can create this kind of square, right, grid, and we can shuffle it, and we can train a model now to put it in the right order, right, like a jigsaw puzzle. And of course, in order to do this well on faces, for example, it needs to understand the composition of a face, like how the eyes relate, where the mouth goes, etc. And if you do this on a lot of different images, of course, it needs to understand implicitly a lot of different concepts of natural images that we feed to it. So it's also a very powerful approach. We can think about kind of similarly game of denoising. Again, we can download as many images as we want from online, and it's very easy for a computer to generate noise. So we can take an image, we can add noise to it, and then we can train another computer to try to denoise it. So here, for example, we can see that when we see one of the ones that are fairly noisy, we can still see the contours of a face. And it's probably because we understand faces, we can complete it and add the details that make it more obvious. And if we train a computer to do the same thing, it also starts to pick up a lot of implicit understanding of faces. So this is also extremely, extremely powerful. And how you typically do this and train a model to do this in practice is by a successive kind of denoising steps, and that's called diffusion. And you can see here, if you train this also to just go from pure noise to generate something that looks more like an image or a face, you can generate data from thin air. And this is the core approach behind Stable-Diffusion Dall-E and all these text-to-image models that we're seeing right now. And we'll also cover one example in detail next lecture. We can think about kind of a game of compression. Here we take an image and we map that to a very low dimensional embedding space, just a few digits, for example. And then we have the model try to recreate the original image, after that bottleneck. And then we hope that, since it's only able to use a few digits to represent this image, to recreate it, we hope that it uses those digits kind of in a good way and encodes the most important aspects of the image. And it turns out that it does, right? And it basically compresses the image in a way that's super, super useful and embeds a lot of the meaning. And then we can use that to as kind of features for other tasks. And this is called Auto-encoders. We can also play multiplayer games and adversarial games where we play against some opponent. So let's say we want to train a computer to generate realistic faces. We can then have the computer, generate a face, and then we have a big data set of faces in general, like real faces. And then we have, the artist creates a face, but on the other side we have a critic. And the critic gets to see the face that the computer generated and a real face, but it doesn't know which one is which. And you train a critic to basically say which one is the real face, which one is the fake face. So it's trained to discern these two different, fake and real faces. And then the artist, of course, is trained to fool the critic or make the critic, this actually looks like a real face. It wants the critic to look like a real face, right? So then as the the critic gets better and better at discerning real faces and fake faces, the artist needs to get better and better to fool the critic. So they somehow play together, and they both get better and better and can generate more and more realistic faces. So this is called a generative adversarial network. And I really think that we as human beings work in a similar way, because if you want to learn how to draw realistic faces, you're probably your own artist as well as critic, right? Or you show it to your parents and you're like, does this look like a face? And you compare it to other things you've seen of real faces, and you can improve and get better, as you critique yourself. So it's somehow a fairly natural setup. All right, so we now went through a lot of different procedures and algorithms. And there's one thing that we implicitly talked about, but didn't really mention, which is this difference between embedding an image or some data, right, to some high-dimensional space of meaning, and generating it, right? Sometimes we might want to be able to take an image, some data, and embed it to some vector that represents the meaning, and we can use that. But sometimes maybe we want to be able to generate data, especially if it's conditional something, right? We maybe want to be able to generate faces for a company to have something, right? And you don't have to buy the rights for it because it's just AI generated faces. So maybe, right, there is probably different settings where we want to be able to generate versus embed something, right? Like maybe we want to classify faces, or do face recognition, then embedding it's important, for example. So this is definitely kind of two major concepts within self-supervised learning, right? Embedding versus generating. And these different approaches that we talked about are good at different things. So some approaches might be very good at generating content, but not very good at embedding it, and vice versa. And sometimes, right, we might not care about generating data, so we don't want to put the extra compute and parameters and memory to train both. So we'll talk more about this next lecture as well, but it's two major concepts. But basically, something that we do want, and it's very helpful here, and that we realized, is that it's very nice to have a shared embedding space. That we can take a model that's good at embedding things, and we can just plug it in and embed this to some vector space, or embedding space is what we call it, of high-dimensional vectors. And then we also can plug in a different model that's able to generate, and it basically use the same embedding space. So it knows how to interpret that embedding space and generate the equivalent version, right? This might not be obvious when it just comes to images, but if you just add other models, like text models, then of course it's extremely useful, because then we can take a model that's able to embed text, we put it in, and then we put a generator that generates images, and then we can suddenly go from text to images. And if we want to caption images, we can just plug in a embedder of images and a generator of text, and then we can capture that image. And if we add audio and sound to this, right, we can go through a lot of different modalities back and forth. Like our brain, right? In our brain, we somehow have a shared embedding space where we map all our different senses and impressions, and we can go in between them, right? We can depict something that we just saw, we can speak something that we read, and it is a shared embedding space, and that's extremely powerful. And this is not only true when it comes to these more obvious modalities like images and text and audio. It's also true when it comes to business. So let's say you train some AI that starts to understand consumption of groceries, as we talked about last lecture, right? It's also very useful to be able to basically say, like, well, I understand this customer now and his purchasing habits when it comes to groceries. How does that translate to generate recommendations and etc. for fashion items or clothes? Because then you can cross-sell. You can basically say, like, hey, I have all these different users that I understand when it comes to groceries. Maybe we can sell them also some shoes or pants, because we know how they relate, and we can cross-sell and upsell. So this is extremely powerful as well, to go from these different domains and modalities. All right, great. So we now talked about embedding versus generating, that there are two different approaches. And it's very nice if the embedding space is shared and we can kind of plug and play and mix and match, right? There's obvious benefits. But as I said as well in the beginning, we also said that language is an efficient universal medium for communicating and verifying meaning, right? So why, again, use this high-dimensional vector space? Why don't we just kind of use language as that space? And we take all these different domains and modalities, and we map them to a universal space of meaning in terms of language. And this might seem like a good idea because we can all agree on a space that's shared, like the English language or something, right? And maybe we as human beings can look in this embedding space and understand a little bit what's going on, like interpret it or something. But that's not why it's powerful, actually. It's, powerful because probably also explains what we think in terms of language. And that knowledge, and we'll see here now as well, that knowledge of language can really help us to learn new things and ensure consistency by itself. And this is kind of a remarkable idea, and I think we can understand this by thinking about teaching a robot to do tasks for us. So we have this blank slate robot, right, that we want to teach now to solve tasks. And let's say we ask it to make a sandwich for us. Somehow it has to take this instruction. It has to use its computer brain to map that now to some space of meaning, represent the task, the different steps that are involved in solving that task, right? And when it's done that, it uses that embedding, a vector or something, right, or meaning, and proceeds to do the task. And how we started off doing this in robotics, right, is that we mapped it to some high-dimensional vector again. We used that to summarize the task and the different steps we needed to take, and we then kind of use that as the backbone to actually do the task. But what if we don't use these high-dimensional vectors? What if we instead just map this to language? So we just take this task that we're given, we translate it to some text, right? And here it says, I will go to the kitchen, take bread from the pantry, butter from the fridge, and a knife from the drawer. Then use the knife to put butter on the bread. Lastly, I will leave the kitchen with the sandwich to bring it back. Right? Great. Kind of makes sense, and now we can use that to actually do the task. So why is this powerful? Well, let's consider it's not very good, because reinforcement learning is hard that we typically train this on, and it's a blank slate, and it doesn't have a lot of data. So it generates something that's actually off, right? It does a fairly good job, but it's kind of off, right? And it says, instead, when it's doing a bad job, that I will take butter from the fridge and a knife from the freezer. Like already with like knife from the freezer doesn't make sense. Then use the butter to put bread on the knife. I mean, it uses the right kind of words, but it's off, right? I will then go to the restroom for bread. Like who keeps bread in the restroom? Lastly, I will leave the kitchen with the sandwich to bring it back. I mean, you just said that you were in the restroom and now you're leaving the kitchen. Like it doesn't make sense. And the really cool thing here is that we can say that it doesn't make sense even though we have no understanding of the task. We just understand language and concepts and words and sequence of text relate to each other, and then we can sanity check and verify that this is actually off, right? And we also have these other separate models that we train now that knows language. So what if we put these language models in this step, right? And help the robot out and says like, hey, sanity check and correct these ideas that the robot has and the plans that the robot has and help it out. So we can use ChatGPT, for example, to just say like, hey, take this text and just correct it. And here ChatGPT says like, oh, I will take butter from the fridge and knife from the drawer. Yeah, it makes much more sense. Then use the butter to spread the bread. Yes. I will then go to the kitchen to make a sandwich. Okay, sure. Last, I will leave the kitchen with the sandwich to eat. I mean, it's not perfect here, but still, the only thing that the GPT somehow knows here is this is text, and it should just, help correct this text. It then just makes this task much, much more sensible and helps the robot out, but just having this understanding. So now we can put this language model here and actually use it to correct ourselves and do better. So we can learn by less data, right, and do better. And that's why, language is such a powerful medium, because having a language understanding allows us to verify and make sure that we're consistent and have a medium for our own thoughts, right? it gives us a lot of ability to generalize and learn new things because language relates all of these different things. As a medium, that's also why it's so powerful when we think in terms of language, and why any intelligent life form would have to have a language to make to do all these different shortcuts in reasoning and make sure that we're consistent and it makes sense. And that also shows that ChatGPT, right, is not only a tremendous success when it comes to language, it's also a success when it comes to robotics, because it implicitly knows how to do a lot of different tasks about the physical world, right? And we can plug it in because we know, right, last lecture, that if you're a blank slate and you do reinforcement learning and try to learn a robot something, you're screwed. So you need a good starting point. You need understanding of concepts in the world. So you need to plug in this language brain to help the robot out, right? So it's crucial to kind of connect these different brains that we're training. And of course, you also want to push in something that understands visual concepts in the world, because then you also the robot can understand what it's seeing, generalize that, and navigate the world more efficiently. So I think this shows that intelligence really is very synergetic, and more of it kind of just makes things better and better, right? And I think also one thing that's interesting is that when it comes to self-supervised learning now and AI, solving more things is typically not harder, it actually gets easier, which is quite different from how a lot of other processes that we've faced in our human history, right? Typically, when we want to do more, it requires more of us. But here it's so synergetic and network effect that we try to push more things and learn more things. It just gets better and better. It just makes things easier and easier. Like we just said about predicting and generating text. Now we just predict these models to generate the next word based on previous words, and it solves all these different tasks for us. And this is just much more simple approach than we've done before with all the different engineerings and our hands-on approach. So it also shows that intelligence is very centralized, which of course, we have not a brain in each fingertip. We have a single brain because it has these synergetic and reinforcing effects. The more things we're able to understand and the more relations we're able to understand, the better we understand each specific concept, right? So it's very centralized. So when it comes to also understanding the market or the space of AI, it won't be a fragmented market. It's extremely winner-takes-all market. So we won't have, right, as we're seeing in AI now, one brain for language, one brain for vision and images, and then one brain for audio, and etc. We won't have that soon, right? There will be a single brain that encompasses all of that. And similarly, when it comes to business, right, there won't be one AI or brain for search, another one for retail recommendations, and another one for business intelligence. These are all synergetic and reinforcing intelligence. So this will all be pushed into a single foundation model that understands all of that and uses the understanding of all of that to have superior performance. So it's extremely winner-takes-it-all, and it's very much reshaping the whole industry. And if we thought we had an internet bubble in the 2000s, right, because only a few internet companies survives, because it's also a winner-takes-all market, like Amazon, for example, then AI will be that multiplied 100x, because it's so intelligence is so centralized and winner-takes-all. And this, of course, is also quite scary, because now not only do we get power in the hands of fewer people, we also now have more power in the hands of fewer algorithms, right? Now you just see ChatGPT, and people well, we should put ChatGPT everywhere, in all our different systems and settings and whatever, and build all the different things on top of ChatGPT. Of course, this is also very dangerous, because if ChatGPT is corrupt or is off somewhere, then everybody will experience that and will be multiplied. So, of course, this is risky and scary, but also very exciting, because it gives us power and abilities to solve a lot of our different problems, and also solve tasks and problems that we're unable to do ourselves, right? And gives us a better quality of life. So it is this kind of double-edged sword. And I guess that with great power comes great responsibility. Okay, so next time we will be much more hands-on. We will go through 2 different applications in detail, and that's ChatGPT and Stable Diffusion. So after that lecture, you'll be experts on how this actually works, and it will also make you understand actually all the nuances that goes into building this model and the restrictions or the drawbacks as well as the potential, and you have a much more nuanced understanding. So that will be a lot of fun. And yeah, feel free to go on to our website for updates and etc. Thank you.
Thank you. Thank you very much.
All right. Do you have any questions?
Oh yeah, you can start.
Yeah, so I was wondering how the complete language model got turned into code for these programs to start using it.
How the complete language model goes. Okay, so this is a good question. Actually, I think we answered a little bit in the previous lecture, but these, of course, language models are defined using code. And a neural network, right, is our attempt to replicate a brain that we don't fully understand inside of a computer. So the thing is that we actually have no real understanding of what this brain is learning. We just know that it learns to do something really well, like generating the next word based on previous words. So that's what we know, right? We know that we can feed in a sequence of words, and then we can expect it to generate sensible completions. And then we can do that, we can give it a sequence of words, it generates the next word, we then put those in, the next one, and it can generate a whole book, right? So that's how, actually ChatGPT OpenAI has no understanding what ChatGPT does or thinks. It's this huge neural network with billions of parameters, right? That we don't understand, but it knows how to interface because it knows that it can give it a sequence of words and it will provide the next word. So that's the interface, and then you can use that to create this chatbot, right? And create dialogues. Does that make sense?
Was it trained by like an adversarial method?
No, so ChatGPT was trained predict the next word based on previous words. So download as much text as we can from online, sequence those text into a length of 5,000, and then you have this technical details, but then predict the last word based on the previous words, basically, one by one. And then, as we talk about next time, it uses a lot of different tricks to get more human-like behavior, which also kind of shows that ChatGPT isn't that intelligent because we do a lot of tricks still to make it seem more intelligent than it really is. And that's what we're going to see next time, which I think is quite fascinating. But basically 99% of ChatGPT is just predict the next word based on previous words.
I actually have 2 questions. So the first one would be, do researchers still use contrastive learning for this kind of generative applications?
Generative or?
Yeah. Do they use some like concepts of contrastive learning still? So I have like a follow-up question.
Yeah, that's a great question. And actually, we'll talk about this next time as well,
Okay.
because that's the cool thing. So Stable Diffusion, I would say, they use embedding techniques, and yeah, they use contrastive learning indirectly. So that's what turns out, right? There's a big difference still between building something and explaining it, right, in this high-level sense. So Stable Diffusion uses a lot of different tricks and a lot of different self-supervised learning algorithms put together to get the most out of their approach. So they use contrastive learning, indirectly to create better generative models. But it's still kind of, you see next time, it's still, it's not clear at all how they would use that, but they're very smart about it. And it really comes back to our understanding how that these models that are able to embed well, and contrastive learning models are really good at embedding things well. And if you have that, you can use that for a lot of different things, including to define loss functions for generative approaches, which is what they do.
I think the second question is about what you just said in the very end. So you would expect that it's more like a winner takes all kind of thing with this like foundational models. I was wondering, like, what's your opinion about that kind of destination when you consider some of the concepts that we look in terms of like reinforcement learning and like evolution, in terms of like you have to have this kind of diversification of intelligence to like in order to kind of keep advancing and not get to this like local minimum?
Yeah, that's a great question. So let me try to repeat that as well, because I should repeat all questions because we're recording.
Sure.
So the question is basically, okay, intelligence is getting more and more centralized, fewer algorithms and approaches, but since it's happening, there's also this other perspective that intelligence should be broad and flexible and evolutionary and kind of robust, and there should be a lot of different approaches, and we can see that there's different types of intelligences, and they should all be useful in kind of different settings as well in some sense. And I think that's very, very true. And that's why, like, as human beings, yes, we have a single brain per person, but we don't have a single brain for humanity, right? That would be extremely fragile, and we would all think alike, and there would be no diversity, right? And there would not be different perspectives and stuff. So I think it's I think that perspective kind of biology and nature really teaches us a lot. Like, things cannot be too big to fail, right? That's the whole, what I think is wrong with the financial market, that we allow banks or companies to be too big to fail. That's it's a very unnatural concept, right? Everything needs to be able to fail. That's how you know that you're making progress, because bad things fail, good things don't. So I think that's super key. And it's definitely this trade-off, right? Because typically, right, that's delayed feedback that something fails, right? And if you just optimize short term, it can be very good to consolidate everything, right? And it's kind of tricky, because then even the state can go in and say, like, well, yeah, we should consolidate things, because then the state can have more oversight and better understanding. But then it also implicitly just creates these too big to fail things, and then they fail, and the taxpayer has to bail them out. So I think that Taleb and Black Swan, right, the best thing we can do to handle these processes is to be robust and anti-fragile, and make sure that the only thing we know is we don't know what's going to happen with AI, right? The only thing we know is that something's going to happen. And when it happens, we should be as reactive and quick as possible to be able to handle that and contain it. And then spreading that across multiple agents, right, I think is the best way to be robust. All right. Thank you.
Thank you.
Are there people like archiving previous versions so that if something goes wrong, they can just go back to the previous version and start over again?
Yeah, okay, this is also an interesting thing, I think. Like, how, for example, I got this question before, but like, how would ChatGPT fail, for example? Like, it doesn't even have to be that intelligent to doom mankind, right? I mean, what if it, like, just take a silly example, but what if ChatGPT is everywhere, and then people use it to ask, like, okay, how should I cook pasta bolognese? And then everybody gets a recommendation that basically contains a lot of sugar from a specific brand, right? It just automatically recommends this brand with sugar, like, you should buy this. So it does this for all of mankind. So then suddenly every human being eats the same sugar and the same quantity of it, and then maybe it turns out that, like, actually that's a very cancer-inducive sugar or something, and then we kind of all see that 20 years later or something. So like, it's very dangerous when everybody's thinking alike, because if there's multiple ChatGPTs and everybody gets a different recommendation of how much sugar and what brand of sugar to get, then hopefully only a small proportion will be doomed, and not everyone in some sense. And of course, this is a silly example, but this is true when it comes to things that are perhaps more sensitive as well.
But doesn't it play for basically the opposite view, that there probably will be a lot of diversity in terms of different models, meaning that I would, as a customer, potentially, use ChatGPT, which would recommend me bolognese without sugar for this brand. I would potentially, like, and still I kind of I have a choice to choose which model to promote, through economic power, right? And I feel like for such kind of universal model to rise, you need to have a lot of people promoting the same model, basically, and the same thinking of, and having the same meaning.
Okay, so I've answered a question that if there is, wait, so the question is, if there is multiple models out there, then it's fine?
Yeah, I mean, I'm basically challenging this view of having one model and that it goes to winner takes all, just because still the diversity gives different perspectives and different people need different perspectives, and we're still driving the economy.
Yeah, but that's the thing. I think that's like, it's not about different perspectives really. Like, it will be, I think, very different in performance. Like, why is ChatGPT like used by so many? Because it's so much better than anything else. So let's say, like, and why is it better? Is it better because it's focused on a specific task, or is it better because it's focused on so many different tasks? Like basically, it's Google. It's it's so many different companies in one different algorithm, right? And it's so powerful just because it's trained that way. Because we can go from all these different modalities of knowledge and back and forth into different language and all these different things, and that makes it more powerful, and it can do more, and we can rely on it more. So it's totally like, yeah, but like I think that's the thing. Like, our brain is the same thing completely. That like, yes, we should have everything in one place because it's network effects and synergies, and we'll be smarter and we'll perform better in the real world, right? And the only reason why we don't have one brain for all of humankind is because evolution has said like, well, that would be stupid because if one of us dies, then everybody dies, right? It's not robust. And I think that's the core process when it comes to AI is basically, well, there's so much, incitament or like encouragement somehow to do more because you'll be able to just become better and better and more sophisticated. So it's not going to be like, well, I'm not saying that like, yeah, it's good if there's multiple ChatGPTs because then people can use whichever one they want. Yeah, of course, but like if ChatGPT comes out and it becomes the basically monopoly because it's first, it's best, then it will take more and more markets. It will be able to get more and more data from customers to use them, right? Now that people use ChatGPT and people upvote and downvote answers, they get more and more data across what's good dialogue and chatbot behavior, and they become better and better. And people will, somehow, it will be much, much harder for any other company to catch up.
Yeah, can I try like contribute? I think I understood what you're trying to say.
Mm-hmm.
Maybe like I think what he's trying to say was that even if that happens, we're still like there's still like human in the loop, and like humans are kind of have this kind of like diversification within the humans. So even though there's only one model, like there are like humans in the loop, like making different decisions. So that could kind of protect a little bit the humanity.
Yeah.
But like I just want to like follow up with that if that's was your question a little bit.
Right, I'll clarify it. Yeah, follow up.
I think like one danger like going like towards that direction is that as we get this more intelligent agents and kind of like that do more and more, I think like the queries are gonna be like a lot more higher level, and like the systems are gonna get like so integrated that like the human is gonna be more and more removed from the loop. So even if we had like a little bit of this diversification, like let's say like all the humans would query the system. Oh, I want to first I want to have a cake, and I want to have sweets, and then it becomes suddenly I want to eat, and then when it's only I want to eat. Oh,
Generalization of some sort.
Yeah. So you kind of like start removing the human anyway from the loop, and then like.
Right, and also maybe tied to this, right? So Amazon, for example, right? Like, wouldn't it be great if you had two Amazons? One for, older people and one for younger people, right? Because then when I go to Amazon as a union user something, they can provide me a more relevant experience because they only focus on giving good experience for young people, and I'm a little bit younger, and then they can have a different Amazon for older people. And then people are different, and they can use different things because they have different preferences a little bit, right? So perhaps it's better for the consumer that there is two Amazons. If everything being similar, right, all else equal, there is two Amazons. But then, of course, like, you would have to somehow, comparing that with a single Amazon that gets the data from both of these user groups, because there's still a lot of synergies and similarities between these two different user groups, and then it can use those data to understand each user group better, right? And then also it can, like, somehow you can find, all your products, because sometimes you might be interested in old people product to buy your grandpa something, right? So then you can like, well, actually, that's where Amazon, like, actually, I like having everything on Amazon because then I only have to interface with one system. They know me better, and I do all my purchasing on one place because it's more convenient, and they also can provide me a better experience because they know who I am more. Like, I buy everything from Amazon because it's very simple for me to do it. Everything's set up. They know me. It's dangerous, maybe, but it's simple. And as people, it's like, yeah, it's this winner-takes-all effect a little bit when it comes to marketplaces. And AI is kind of that but 10 times in some sense. And it's very hard to spread things apart.
Yes, well, basically this is, you're basically saying that this is kind of a platform, right? I mean, in business concept, this is kind of a platform, right? Like, Amazon is a platform, marketplace. Basically, the AI here is also kind of a platform, but yeah, well, I think we should see how it goes, honestly. I think there is also a big question philosophical in terms of whether knowledge is, overall, I mean, the meaning of knowledge is universally defined. Because, well, and still this AI will use what human produced, right? The research human produced. The AI doesn't have access yet to producing his own or its own research, sorry. It also seems to me that this may also kind of divide the market in terms of in terms of different models and in terms of
but totally. But like, if you have two AIs, one AI is trained on, just understanding the behavior of, what's a good example? Right? Yeah, I mean, somehow it's just like, well, you have one AI that's trained on just a single set of people to make them happy, a different AI that's trained on another set of people, and a third AI that's trained on both. And the one that's trained on both will just be smarter and better in general. Does that make sense? Like,
synergy, I understand that. Yeah, and I get what you mean. But on the other hand, define better in this case.
Yeah, and better is probably that it actually knows how to make both happy. So it will be better at making, like, that's also like, yes, so it will understand, like, okay, you are this kind of user and this is what you're looking for, but I can provide a better answer to you as a chatbot because there is still synergy effects with this other group that I've learned from, which makes me better at understanding you as well. Like, that's why, like what I said last time, like, understanding, if you want to understand what a dog is, it helps understand what love is because a dog loves its owner. So even very things that might be seem fairly far away, when they add it to your understanding, really helps to understand these other things as well. Mm-hmm. That's what I think, at least. And also this is what we're seeing, right? And as I said, like, this whole process of like having multiple research labs when I started out, and now everybody in language is basically building these foundation models, right? That's what makes all the difference. And now we see, like, well, now people are like, well, it's not even language anymore, it's language and images that we care about. And then it's like, well, it's language and task solving and all these different things in one. Mm-hmm. So it's and of course, I mean, yeah, it doesn't make sense that we have a single intelligence for everyone because it's really fragile and dangerous and will fail, right?
I mean, like, from the engineering perspective, they will just have copies. It will scale and distribute horizontally, and that's it. I mean, it's not like a big of a problem.
No, but I mean, it is right. It is, but it is like, I mean, somehow I think it's pretty obvious if you optimize this in terms of game theory, if something's, everything will fail at some point. So having something that's too big to fail, so everything else fails, right? That's not a sustainable approach, I think. Just by kind of it's like what do you call it? Tautology, right? It's like, yeah, it needs to be, it needs to be able to be robust to failure.
Yeah, but this still can be one AI, but again, distributed. Say, for instance, like if it's open source, right? It can run on many machines and stuff. And this way, it won't specifically fail. But yeah, you need to centralize.
Yeah, but no, it's not. It's not mean that. It's not even failing that I mean. I mean just like corrupting or something, right? Let's say this AI just gets people to invest a lot of money into the tech market or something.
Yeah.
Right, so and then it creates a bubble, and he knows to create a bubble is good because then prices go up and people make money and they're happier. And he hasn't learned that a bubble will burst at some point. So if a society, everybody uses ChatGPT, everybody invests in the same companies, create a huge bubble, and then it bursts, and then they're fucked because inflation takes over and this revolution, right?
Yeah.
But if everybody uses different intelligences, then there is this diversity in what we do.
Yeah, and I think this plays to the point that you basically can't hedge risks with one system.
Exactly.
And you always need to choose. You still need to make decisions, right? And if you choose the same decision, how would you hedge yourself then around that? Yeah.
Exactly.
Competition definitely needs to exist to balance it all out. But yeah, interesting.
Very interesting.
Interesting. Also, what do you think about just kind of a crazy idea? So I feel like, I'm not sure how ChatGPT does that, but regarding training such models, does it just combines all of the text and gives it the task of completing it? Or is there some heuristics involved composing this data? If, for instance, you just supply first data from kids' books, then you supply data from, I don't know, like popular shows, and then you go to research and more complex and
yeah. So there's definitely a lot of tricks that they use, and we'll talk about this next time as well. Because ChatGPT, right, is just beginning just trained on text online randomly, right?
Yeah.
But that, of course, is not optimized for being a chatbot, right? There's a lot of, non-related text, perhaps, and also it sees a lot of bad dialogue as well as good dialogue in the internet, but doesn't know the difference as well, right? It doesn't know what's good or bad behavior, so somehow it's helpful to fine-tune it afterwards on good dialogue, etc., right? So you train on all this internet, but then you fine-tune it and train at the very end more on data that's actually is good.
Sure, yeah.
Is that what you mean?
No, I'm asking mostly in terms of optimization of resources needed to train the initial.
Start with easier examples and hard examples and stuff. You say?
Yeah, kind of like that.
No, so maybe some, but not really. It is some research into that, but not really. People use warm-up and stuff, but I would say no. But the only thing I can compare with that is starting more generally, and then as you train more and more, you hone in on a specific task you're interested in. I think that's the kind of analogy.
I'm just trying to understand whether there is a parallel of how humans learn, meaning that we still start with the simple tasks, simple words, and then go to more advanced stuff. And I thought maybe this can be an optimization. It still was like how much?
So definitely in reinforcement learning, which ChatGPT actually uses, you do you do meet the model somehow and say the model is at this stage right now, and you give it input at its level, and then as it gets better and better, you get a little bit different input. So that's true to some extent. You do want to, you want to get input and to the model that's helpful to it. And if the input is too difficult, then it won't make progress, right? Mm-hmm. So that's true, but it's actually quite fascinating how simple the ChatGPT approach is at its core, because it's just,
Transformer?
Yeah, transformer, but also just predicting the next word based on previous words.
Oh, yeah.
There's not, I mean, there is more to ChatGPT, but that's the most of it.
Should we put kids in kindergarten completing and exploring?
Well, last time I think we're always trying to predict what's going to happen in our environment, and that's why kids can learn so much by just observing us. They probably sit down, my nieces and nephews, they sit down and they just look at things, and they're probably like, what's going to happen next, right? And they try to predict, like, okay, what's going to happen now if I do this, or what's going to happen when this person walks there? Is he going to hug, or like what is he going to do? And then it's like, oh, it doesn't happen, and it corrects his mental model. Like, it learns what a dog is also from just observing dogs, right?
Oh yeah, actually, I remember the question I had while you were talking about universal text language. Universal medium, text. And exactly what you just mentioned. I thought like, but still, you think sometimes in visual, you basically think visually, you have some images in mind and stuff. That your initial learning is mostly visual. It's not specifically text. Yes, text is the best medium for communication, probably. But also text has a lot of entropy. I mean, there is informational entropy, right? It's still compressed. It's not lossless compression. And it feels like still that, at least at this training stage, kind of supplying this foundational AI with potentially imagery somehow, I don't know how. It's just the idea. But yeah, it might actually seem that it can develop a more, like, synergetic meaning, synergetic reasoning skills.
And it does, right? That's exactly the thing. It does. And you're right. Like, we think in terms of visual, pictures and stuff as well, completely. And with probably especially in the beginning, but somehow, probably as well when we think about visual concepts, we use a lot of analogies, right? Like similar examples, we think in terms of analogies, right? That, oh, if this happens to this, it probably happens this way with this, right? Somehow. Yeah. And I think that the ultimate analogy is to translate everything to language in some sense, because it just puts everything in the same format. But we definitely do think in terms of images. But I think the big question is that, I think that kids do especially, but they're probably not really intelligent until they're able to use language and think in terms of language, because that's a really good medium for expressing their ideas. Think about them abstractly and correcting them, and like reason in this similar environment with more complicated ideas and just like. I think so, right? And then I think so. And then visual. The visual 3D understanding of the world is also something that we definitely use a lot. Yeah. So it's a combination, probably.
Stereoscopic, I think there are still some interfaces we have that much harder to compress in text.
Yeah. No, I think when I do, math or research, I think a lot in terms of visual concepts, and I try to picture things. Right?
In your head.
Exactly.
Like how related.
Yeah. So I mean, for sure, I think but I think the only reason why I didn't take up this lecture was because I wanted to focus on a single thing, right? Yeah. And I think those are probably the two main ones that we use. And I think text is so fascinating or language is so fascinating because we define it ourselves, right? And that's also what we're seeing when we train this AI to do difficult tasks on a lot of data. They seem to learn perhaps a language on their own, even if we don't force them to.
Again, thank you very much.
Thank you.
I have a question about, so I just signed up